Yeah. So hi all, welcome to the extra live session for AI SMPS. I hope my audio is clear and my screen is visible to all.
Yes.
Okay, great. Thanks for confirming. So yeah, I have a couple of questions prepared um, based on the feedback that I received in the past couple of live sessions. So there were a lot of questions that you guys wanted to have a discussion about. I'm not sure if we are going to have enough time to discuss all of those because some of the requests were going through complete assignments or a big chunk of the assignments in the current course. So we'll see. I have tried to focus on the topics that were discussed in the initial part of the course, which includes starting from with the very initial week 1, week 2, the state space definitions, DFS, BFS, the different versions of DFS, A star, um, applied, SMGS, sparse memory graph search, and all those topics. I would prefer to prioritize those because the later weeks 9, 10, and 11, and those they are still recent, and I hope that some of you, if you have missed the live sessions, you can revisit the lecture videos and the YouTube videos of the live session, and hopefully that will help. But yeah, depending on how much time we have, we'll decide to uh, look into those. But for starters, let's get started with the topics from the initial few weeks of the course till the middle of the course. Okay. So one of the requests was to look into the week 2 assignment. Um, so the request that I received was questions 2, 7, and 9. I wasn't sure which assignment it is referring to because there are two assignments in week 2. But overall, they cover these topics, which is state spaces, valid and invalid states, and the different versions of DFS. So I thought let's go over each of those. Okay. So let's first look into week 2 assignment 1. Um, so I'll skip the first question because it's a pretty recall based question. Let's go into the next question, which is based on this interesting game called Palanguri. I hope I'm pronouncing it correctly. Um, so it's a two-person game played in a lot of states of India as well as in other countries like Sri Lanka and Malaysia. Essentially, what you have is you have three cups. Okay, each cup holds 0 or more shells or seeds. Okay, and a single move involves three steps. We first select a non-empty cup. Okay, any non-empty cup. We remove all the shells from that cup and then we distribute those shells in a round robin manner. If I have to draw this, it will look something like this. So let's say you have three cups. Okay, A, B, and C. This has, let's say, 4 seeds, this has 3 seeds, and this has 1 seed. Okay, so you will select one of these cups. Let's say you selected cup B. Okay, you will take out all the 3 seeds from cup B, which will lead you to this configuration wherein cup A has 4 seeds, cup B has 0 seeds because you took all those out. Okay, and the 3 seeds are lying outside over here, and cup C has 1 seed. Now what you will do is you will distribute this seed in a round robin manner. Okay, round robin meaning you will keep moving on in the direction A B C A B C A B C, depending on which point you start from. So if you decide to start from B, or you decide to empty B, you will first put a shell in C, and then in A, and then in B, and then in C, and then you'll keep on repeating this process. So this is what it will look like after you put the first shell from B. So A will still have 4 shells, B will still have 0 shells, C will now have 2 shells because you put 1 shell, and then you have 2 more shells in hand outside. Next, you will put this shell in A. Okay, so you filled C, now you will fill A. So then you will have 5 in A, 0 in B, and 2 in C, and you will still have 1 shell remaining. In the next step, you will put the remaining shell into B again, okay, because you already filled A. Before that you had filled C, now you're going to fill B. So you will have 5 in A, 1 in B, and 2 in C. Okay, so going from this state to this state, this whole process is one move. Okay, this is the game. Now let's go back to the question. So what it says is, for example, let's select cup A, okay, and remove all the shells from cup A. Let's say it has n shells, and then add 1 shell to each cup in a round robin sequence. So BCA, BCA, so on until all the shells are placed. So if you select cup A, we will follow this sequence of round robin BCA, BCA. If we select cup B, we will follow CAB, CAB. If we select cup C, we will follow ABC, ABC. Okay, this is another representation that has been showed in a diagrammatical manner. So I hope the problem setting is clear. Any doubts about the problem setting itself? Okay, I am assuming that the problem is clear to everyone. So let's now proceed to the
Yeah.
So we are given this state space 34. Okay, 34 is just a number. I don't think it has any relevance to whatever we have over here, or it may have, I don't know. But basically what we are told is that we have a beginning state 004, which is over here. Okay, and we have to discover the neighbors of 004, which will be called the move gen of 004. Okay, so if you remember from our live session discussions, move gen is essentially telling us what are the states you can go to from a given current state, right? So from 004 we have to find out what are the states we could go to, and for that we have to basically see what are the possible moves we can make. For example, in 004 there are no seeds to distribute in either A or B, so the only option is to distribute the seeds in C, right? And that will lead you to a certain state. For each new state X, we again call the moveGen X to generate the neighbors of that particular state, and we have to keep repeating this process until no new states are discovered. So this question in a way also gives you an idea of how do you come up with this state space given a starting state. Okay, I remember this was one of the questions that were also raised in the live session when we were discussing these kind of questions. So I hope this gave you some idea of how to proceed with building a state space. Okay, and for the beginning state 004, the state space is already given to us. The first question asks us which of the following valid states are the valid states in state space 34. So the answer is already visible here, but I would like you to give your thought processes behind or justifications behind why 400 and 202 are the correct answers and not 360 and 212. So anyone can feel free to unmute themselves or write in the chat box.
They are not in the graph.
Exactly. It's as simple as that. They are not in the graph. So given 004 as the initial state, you were not able to find any such state like 360 or 212, which could be reached by any of the intermediate states. Just because of that reason, they are invalid states in this particular state space 34. It may be the case that you can reach 360 and 212 through some other initial state. That is not our concern as of now, but because of that simple logic that they are not present in the graph, they are not valid states. And 402 and 202 are, because 400 is present over here and 202 is present over here. Okay, so the next question is, from the state 1 to 1, which is over here, which of the following states can be reached in exactly one move? Again, you can only answer it by looking at the graph itself.
Yes. Maybe 310, 013, 400.
So 031 and 220 are correct, but 310 is leading to 1 to 1. 1 to 1 is not leading to 310. Okay. So if we have a look at the directionality in this figure, maybe I'll zoom in a bit. From 1 to 1, I hope the question asks us about 1 to 1. Yeah, it's 1 to 1. We should look at the outgoing edges from 1 to 1, which is 202, 031 and 220. Right, so 3 outgoing edges from 1 to 1.
031.
031, yes, that is also one possible state you could reach. And so 031, 202 and 220 are the 3 states you could reach from 1 to 1. And this is a multiple select question. Another thing I would like to point out is that sometimes the question is framed in a way that this list of options that you have to choose from, this may not include all the states that you could reach from 1 to 1. For example, here from the graph we see that there are 3 states that you could go from 1 to 1: 202, 031 and 220. It might be the case that the options will contain only one of those or two of those states. So you should select only those one or two of the states that could be reachable from 1 to 1, even if not all the states that could be reached from a given state 1 to 1 is given in the option list. Okay, so just be careful about that. Is it the same question that they have repeated? From which of the following states we can reach 1 to 1 in exactly one move? So now we have to look at the incoming edges into 1 to 1. So can anyone tell me what will be the states from which we could reach 1 to 1 in exactly one move?
013.
Correct.
400.
400, correct. And one more?
310.
310, perfect. So 3 incoming edges: 013, 400 and 310. Okay, so that is question 4. From the state 004, the minimum number of moves required to reach 400 is? From 004 to 400.
Four two, 211, 211 to 310,
Okay.
310 to 301, 301 to 446.
Okay. So 4 moves, right? Let's check. Yeah, that is 4 moves, and that is very precise. Okay. State true or false. In state space 34, there exists a pair of states x and y such that the move gen x contains y and move gen y contains x, which means you can go from x to y and y to x. Is there a cycle?
That is not possible. R are single direction.
Yeah, that is why the answer is false. So you can also verify that using this graph over here, that there is no such pair of nodes. Okay, so the answer will be false. In state space 34, every state is reachable from every other state in one or more moves. This should be or instead of one or more moves. The answer given is true. You can verify that. You can start from each state, let's say from 004, and see if you can reach all other states from here. And you can do that for every other node as well. Okay, likely this kind of question is a bit of time taking question, and it's unlikely that they will ask something like this in the exam. Usually they should ask questions that are doable in a very short time. Okay, because you have limited time in the exam, but still for the sake of understanding you can go through each of these nodes exactly and see whether all are reachable or not. The last two questions are to select true statements. All states and state transitions in graph 34 are valid, which makes sense because we made sure of that, right, while constructing the graph. And all states from state space 34 are present in graph 34. Okay, this is also following from the logic given over here. Yeah, you can again verify whether all possible states that are reachable from this beginning state are included in this whole graph. So that was assignment 1. Any doubts remaining in this assignment? Okay, no, that's great. This is also a fairly simple assignment, so I hope that's clear to all. Let's move on to assignment 2 then. Okay, so this is our typical setting of a graph wherein we are given this move gen table and we have to apply different search methods. We have discussed DFS and BFS at length, so I am going to avoid discussing or going into details of DFS and BFS. Rather, I would prefer to focus on the variants of depth first search. Okay, so but if there are any doubts in the DFS and BFS algorithms, please feel free to let me know. Okay, so when depth bound depth first search with a depth bound of 3 is applied and it finds the goal node, that is when the goal test returns true, what are the nodes present in the open list? I know the answer is already given here, but still I would encourage you to try to solve it by hand and tell me what the tree looks like. Okay, and then we can have a discussion of the solution. So through overview of DFS and BFS, I would first encourage that you also revisit the previous live sessions because there we have gone in depth into DFS and BFS. But yeah, I can give an overview. Basically what we do is we have two lists, open and closed, okay, in both cases DFS and BFS. In DFS we use what kind of a data structure? Can anyone tell me what data structure we use in DFS?
Stack.
And in BFS?
Queues.
Queue.
Okay. Just give me a moment, yeah. Yeah, so that is that. And then and then basically what you do is you insert the elements into that data structure in the order defined by the move gen. Okay, you start from the start node and then follow the move gen to gradually insert the elements into the data structure corresponding to which algorithm you use. If it's a DFS method, you use the stack. If it's a BFS method, you use the queue. And then you pop elements from that and then put it into the closed list, and then you repeat this process until you reach the goal node. Okay, so DFS we will actually revisit because we are going to look at the variants of DFS, but for breadth first search alone I would encourage you to revisit the previous lecture videos. Okay, So DBDFS, it is essentially DFS, but you are given a limited depth. Okay, here the depth is given as 3. So you will limit your search tree till depth of level 3. Okay, so I'll just wait for a minute for all of you to try to construct your depth bound depth first search tree, and then we will discuss the solution.
Meanwhile, can I ask one question?
Yeah, Shiva, please go ahead.
So, in the answer, they are asking sometimes the nodes in the open list or closed list. So, in the practice assignment, they given the answer from tail to head. In the assignment, they followed head to tail.
Okay.
So, there is ambiguity. So, which order we have to follow in the examination to give the answer?
So here they have given head to tail.
Yes, but in the practice assignment, they give an answer tail to head.
Okay, is it
Practice, yes.
Okay, got it. So whatever the question says, when you get it in the exam, if it says head to tail, report it in head to tail. If it says tail to head, report it in tail to head manner.
If they not mention anything, then?
No, they will mention. If they're not mentioned and didn't mention anything, then that will be an ambiguity in the question. You can ask the people who would be there to clear that ambiguity. That shouldn't be there. It should be specified.
Right. Thank you.
Yeah. Okay, so let's try to solve it. Okay, so the first thing that we'll have to look at is the move gen. Okay, we'll start from the start node, and this is given to us. From S we can go to A, B and C. Okay, so let's write that down. From S we can go to A, B and C. Okay, so this is depth 0. This is depth 1. Okay, and we are going to extend it till depth equals to 3 because that is the limit given to us. Now amongst A, B, C, this is the order in which we were given the move gen function gave us the nodes. So which of these nodes will be inspected next?
A.
Correct. So now let's have a look at what is the move gen for A. and A says C, E and S. So out of this, S is already in the closed list, correct, because it's already been expanded. C is already in the open list, right? So the only element that we will explore is E next.
E.
Yeah, so let's add E. Okay, now this is depth 2. Okay, and because we are proceeding in a depth first manner, which node will be expanded next?
E again.
E again, right? Because if you imagine the stack currently, it would be like this, E would be at the top, at the bottom of E would be B and then C, correct? So E will be expanded next. So let's look at the move gen for E. So move gen for E says A, B, F and H. So A is already in the closed list now, B is already in the open list, F is still unexplored, H is still unexplored. So what will we do here?
Both F and H.
Yes, both F and H will be added as children of E. And this is depth equals 3. Okay. So now we have explored E. Which node will we look at next?
B.
Is it? We are proceeding in a depth first manner, right?
Yes.
So after E, which node will be inspected?
Also. But depth 3, right?
So we have arrived at depth 3, but still we have to check whether we reach the goal node or not, right? So yeah, I mean we will go to B
Then F.
eventually, yeah, but the
Yes,
intermediate step will involve F and H in the stack like this.
Yes. Got it.
Yeah, so we will inspect F. F is not the goal node, so we will pop F and we will go to the next element in the stack, which is H. H is also not the goal node, so we will pop H as well, and then we will go to B because B is the next element. Okay, so then we will do move gen B.
Yes.
And that will give us D is new element, so it can be added. E won't be added because E is already in the closed list. H is already in the closed list. S is already in the closed list. So only option is to add D. So we will add D next. Okay, and next we will visit which node? D, right?
Yes.
Yes. So let's have a look. Yeah. So let's have a look at the move gen for D. So for D we can, so B is already in the closed, C is already in the open, G can be added. So we will add G. And at depth 3 we have found the goal node. So this is the search tree for DBDFS with depth bound 3.
Your screen is not visible. Yes.
This is what I was showing. Okay, so based on this, let's look at the questions that we had. So first of all, is the tree construction clear to everyone? Any doubts there? Okay, that's great. So I will also point you to a resource over here. Okay, so if you go to lecture materials, you will find partial solutions to or solutions to the practice assignments at least. Okay, so let me show you that. Yeah, here you have been given the depth bound DFS for different slightly different graph. Okay, you can visit this as well. Okay, and you have also have the traces given over here. So I know most of you would be aware of this already, but just in case some of you are not aware that this exists, please make full use of these kind of resources. Okay, so for most of these, if not all of these practice assignment questions, you would find some or the other solutions over here. and it is highly encouraged that you make use of these.
Sir, I have a doubt here. Can I ask now?
Yeah, please go ahead.
Sir, if you apply, let's suppose DFS or BFS,
Mm-hmm.
if they are asked a path followed by the DFS or path found by the BFS, that is, we will agree.
Mm-hmm.
If in case they will ask what is the optimal path found by BFS, if it is the same or different.
So each algorithm will be limited by how optimal it is, right? So whichever path is found by that algorithm, be it BFS or DFS, to reach the goal node, that will be the optimal path that it has found. If it has found a path that is longer than the shortest path, then that is a limitation of the algorithm itself. Okay, so that is the path that you will have to report. If they specifically ask the path returned by BFS, if they ask what is the optimal path in the whole graph, irrespective of whichever method you have to use, then you should always report the path with the lowest cost, which will be returned by a method like a star, which always returns the optimal path, given that it has a admissible and consistent heuristic.
Yes, sir. According to that, I have followed like that only.
Mm-hmm.
But in the answer they mention only optimal path as a path solution.
Okay, so it might be the case that BFS in that case is able to find the optimal path. That can also happen. So that's why they maybe asked you to report it. Is that the case?
Maybe, sir, but in the search process, we reach the goal with a separate route.
So the
After reconstruct the optimal path, sorry, what I can say.
so let's say you are applying BFS. Okay, from the start node, were you able to reach the goal node?
Yes, sir.
Okay, and is that path the least cost path in the whole graph?
No.
No. Okay, so then that is the path returned by BFS. It is non-optimal in that case. Okay, in that case, BFS has failed to find the optimal path.
Okay, sir.
Okay. To answer a couple of questions in the chat, Dhanalakshmi, we will try to cover week 9 question 11, but I will first, like I was mentioning in the initial part of the live session, I will prefer to focus on the topics from the initial few weeks, from weeks 1 to 5 of the course. Okay, so that it's kind of a revision. If you have time remaining, we will have a look at these questions. Himanshu, so the questions that you will be asked in the exam will be similar to the questions you have been asked in the different assignments. So I think in the previous live session also one of your colleagues had mentioned here that in the discussion forum, Bhaskaran sir has given a breakdown of the different types of question that you can expect, different marks of question that you can expect. Please have a look at that as well. And through so basically the elements which are not explored are added in the open list. So elements that are not explored are added in the open list. Elements that have already been explored are added in the closed list. Okay, this is always true. Okay, so let's have a look at the questions then. Where is DBDFS? Yeah, so the open list, when our algorithm finds, DBDFS finds the goal node as per our search tree that we constructed, only G and C were there, right? You can even consider that we already arrived at G, so at that point only C would be remaining in the open list. So only, sorry about that, only C or GC, both are acceptable answers. In this case, they are even taking in CG as an expected answer. Okay, and list the nodes inspected by DBDFS. Okay, so for that we'll have to look at the search tree again. So first we looked at S, then we looked at A, then we looked at E, then F, then H, then B, then D, and then G, right? So S, A, E, F, H, B, D, G. That is what is given over here as well. What is the path found by DBDFS? So the path found will be different from the path that we explored. right? We explored all this depth, but this depth didn't give us the answer. So we retraced and went back to this particular depth, and this gave us the answer. SBDG is the final path that we found, which is also what is given over here. Okay. Any other doubts in DBDFS?
So in question number 9,
Yeah.
actually we have that final node GC or C and then CG. Why here simply that second answer C you written? Then why can't we also have that answer G alone?
No, G alone is not possible, because when you are reaching the goal node, you also have an unexplored element in the stack, right? So your stack, when you find the goal node, is looking something like this. Your goal node is at the top of the stack, and then you also have C at the bottom, which is still unexplored. We reached the goal node before we could explore C. So C is still in the open list. That's why you also have to report C. Okay, not just G. You can even omit G, but you still have to report C.
Okay, sir.
Okay. Himanshu. No, unfortunately, this time we had only one TA, that is myself taking the live sessions. But yeah, you can. You can revisit the lecture, the recordings of the previous live sessions. Hope that helps. But please don't rely solely on the live sessions. Please also visit the lecture videos. That should be helpful as well.
So live session link also there, sir. The previous live session link also there, sir. YouTube
everything
link.
is there on the Swayam portal.
Okay, sir.
Yeah, over here. You can click on this one. This will lead you to the recordings of all the previous 12 weeks.
Okay, thank you, sir.
Yeah. And yes, Pujita, we will discuss the branch and bound TSP part 2. I will especially focus on that, because while I was trying to solve that myself, I was feeling that it's quite tricky. So we will have a discussion of that. Himanshu, I'll again emphasize that yes, assignments and the practice assignments definitely you should solve. Live session questions also you should try to solve, but please don't rely solely on these couple of resources. If you have time, please do watch the lecture videos, because that is where you will build the concepts. Okay, in the assignments and the live sessions you will apply the concepts, but you will learn the concepts in the lecture videos by Professor Khemani. Okay. And Dhanalakshmi, yes, we will try to cover that, but I am not giving my word for that as of now. Okay, so we covered DBDFS. Let's have a look at the two other variants of DFS, which is depth first iterative deepening with cyclical refinements and without cyclical refinements. I suppose I don't have a question from that over here, but in any way, we can still revisit that. Okay, so let's consider the same moveGen function. Okay, this moveGen function itself, and let's try to consider the depth first iterative deepening tree. Okay, so depth first iterative deepening essentially is applying depth bound depth first search with different depth limits in an iterative manner. So basically you will start with depth equals 0. This is the first iteration. Okay, then in iteration 2 you will increase your depth to depth 1. Okay, In each depth you will construct the depth bound depth first search tree. Okay, if you found the goal node, you will stop with that iteration. If you didn't find the goal node, you will move to the next iteration with an increased depth. Okay, so let's construct for depth equals 0. For depth equals 0, we will have only the start node, right? So definitely we haven't reached the goal node, so we will have to move to iteration 2 with depth equals 1. Okay, and this is what the tree will look like at depth equals 1. A, B, C. We still haven't found the goal node, correct? So we will move to depth 2. So first we will have the start node, then from start node we could reach A, B, C. Okay, so this, and after ABC we will expand A, right? Because A is at the beginning, so after A we will expand A. A will lead to C, E and S. Now this is where the difference lies, depending on whether you are using depth first iterative deepening with cyclical refinements versus without cyclical refinements. If you are doing cyclical refinements, you can include S and C again, because they are being revisited after being seen either in the closed list or the open list. So you could write CES okay, and then you can keep expanding this tree, but this is the limit of your depth, right? This is depth 0.
Screen.
Oops, yeah, sorry, thanks for that. This is depth 0, this is depth 1, this is depth 3. Okay, and you will keep expanding the tree. I haven't drawn the full tree. Okay, here you see none of them are goal nodes, so now you will go to B. You will expand B. What is there in B? B, you have D, E, H, S. So we'll write all of them, D, E, H, S. Oops, this should be 2. Again, none of these are the goal nodes, so then you will refine C and
So screen.
yeah, I just noticed that. Sorry for that. And then when you expand C, you will have A, D, F, H, S. So all of these you will have to write again. A, D, F, H, S. You didn't find the goal node, again in depth equals to 2 as well, so you will move to iteration 4. Now with depth equals 3, and you will again construct the search tree for that as well. Okay, and if you find the goal node, you will stop here, or else you will move to depth equals 4. This is where cyclic refinements are allowed. If cyclic refinements were not allowed, then you need not reconstruct all of them or revisit all of them. For example, here the moveGen function said that from A you could go to C, E and S. So C is already in the closed list, in the open list. S is already in the closed list, so we will only write E. Okay, and this way you will keep expanding. So I see a couple of reactions. Is there any doubt, any issues you guys are facing?
No, it is not for that clarification. They are discussing regarding exams.
I see. Yeah, so yeah, maybe you can reserve the discussion for the end of the session today, okay? Because the reactions might be a bit distracting. Okay. Yeah. Um, yeah, should be depth equals to. Thanks for that, Lakshmi. I have corrected that now. And yes, again, Pujita, I will see if we can revisit week 12 and all those, the later weeks. But as of now, let's focus on the initial few weeks.
Okay, sir, but line drawings are not discussed in previous week 12 live session.
Yeah, I understand. Let's see if we can have a discussion on those. Okay.
Okay, sir.
Yeah.
Thank you.
Okay. So that was the two different versions of depth first iterative deepening, DFID C, which is with cyclical refinements, and DFID N, which is without cyclical refinements. Okay. And again, I'll point you to this resource that I was mentioning earlier. Okay, this is again from the lecture materials. Okay, so you are given a simpler graph and you can see the different DFID trees constructed at the different depths 0, 1, 2, 3. Okay, so here you are depth 0, depth 1, depth 2 and depth 3. Finally you reach the goal node over here. So I'll actually let this be here for a minute and then I'll go to the next topic that we had to discuss. So Aparna, I don't have solutions for all weeks. I'm only discussing this on the fly. Like I have prepared the solutions, some of the solutions today, and yeah. So yeah, I don't have the solutions for all weeks. But if you require any solutions for any of the assignments, please post whatever solution that you have come up with in the discussion forum, and then. Hopefully, if there is any issue with that, it will be addressed through Bhaskar answer or one of your colleagues. Yeah, I'll go back to the previous screen as requested.
1 minute here in the third, fourth one, D3.
Yeah.
Only SA it is given. Why not B? Yeah. Wherever your cursor was there, no?
Here only.
Below
Right?
that one. Yeah, below that SA and B is not given.
Okay, it should have been there. I think this might be a mistake.
No,
It should
no,
have.
sir. Sir,
Uh-huh.
before reaching that depth 2S, B is already there as a child of a depth 0S. So, the children which are in the open are not added.
No, if you see on the right side of B, you are having for B.
Yeah. Here.
Again A and B is there.
Yeah. If it's cyclical, I think all of them should be included. If it's
No,
non.
sir.
Okay, is that the case?
Algorithm, if we follow, then B will not be there.
I see. Then it shouldn't be here as well, right?
Closed nodes are, sir, closed nodes can be repeated, but open nodes cannot be repeated. Here we don't maintain the closed list. So when we reach that S right side, then upper B will be in the closed list, not in the open list.
Okay.
So when on the right side S, there is a B as the child also.
Okay, thanks for pointing that out. So if we follow that, then this graphs is correct. Okay, so yeah, thanks for pointing that out. Even I wasn't fully aware of that. So yeah, please verify this using the pseudocode given in the lecture videos or the lecture materials, and follow the appropriate instructions as per the pseudocode. Okay. You can find this in one of these materials. This is the same graph without the repeated cyclical refinements. Here you have a different tree, and you reach the goal node at depth equals to 4 as opposed to depth equals 3. Okay, so I'll again wait for a minute before we move on to the next topic. Okay, I hope these initial few discussions we had on DFS and the variants of DFS is clear to everyone.
Yeah.
Okay, great. So now let's move on to the next topic that I had in mind. So yeah, based on these few requests, we have discussed the state spaces, valid and invalid states, and the different variants. Now let's go to the TSP branch and bound practice assignment, because that was a very highly requested doubt. Okay, so first let's go over the instructions one by one. Okay, it's a very detailed set of instructions. Okay, let's go over that one by one to clarify things. So an edge is a directed, unidirectional or one-way link from one city to another. Okay, so if you have 5 cities over here: Chennai, Goa, Mumbai, Delhi and Bangalore. If we have to draw that, it will look something like this. Let me first erase these. Yeah, so you have 5 cities: Chennai, Goa, Bangalore, Mumbai and Delhi. So something like this is an edge. Okay, for example, two edges, Chennai to Bangalore and Bangalore to Chennai, these are different links. Okay, so this and this, these are two different connections. This indicates Goa to Chennai, this indicates Chennai to Goa. A segment is a bidirectional two-way link between two cities. For example, Chennai to Bangalore contains two edges, Chennai to Bangalore and Bangalore to Chennai. So if we consider these both of these together, this together will be a segment. Instead of all these, if I just write this indicates this includes both the connections Goa to Chennai and Chennai to Goa. This is a segment. Okay, segment consists of two edges. A segment is symmetric. Okay, makes sense. So if there is a segment Chennai to Bangalore, then there have to be two edges. There have to be two edges, and also there has to be a segment from Bangalore to Chennai. Okay, both contain the same set of edges. The notion of directed edges is not necessary, but yeah, for first timers, directed edges makes it easier to visualize the method. So yeah, you can use that. Branch and bond algorithm starts with a selection of 2n directed undirected one-way edges that satisfy the lower bounding invariant. Okay, what this tells us is that we will look at the distance matrix given to us, okay, which is over here. For each city, we will have a look at the two edges with the minimum cost in that row. Okay, so for example, for Chennai, the minimum cost edges would be which ones? Can someone point it out to me?
Chennai, Bangalore, Chennai, Goa.
Correct. Chennai, Bangalore with cost 360 and Chennai, Goa with cost 800, right? So you will make a note of these two. Okay, let's actually write it down. So for Chennai, we had Chennai to Bangalore and Chennai to Goa. Remember, for every node you will have two edges, right? Because in the final tour, TSP tour that you want, each node would be having two incoming or outgoing edges associated with it, right? When you build the whole tour. Let's also note down the cost associated. Okay, so for Chennai, it was Chennai to Bangalore with cost 360 and Chennai to Goa with cost 800. Next city we will have a look at is Goa. So here the minimum two costs are which ones?
Goa, Bangalore, Goa, Mumbai.
Correct. Goa, Bangalore and Goa, Mumbai. So we'll make a note of that. With cost 570 and Goa, Mumbai with cost 590. Next city we'll have a look at is, let's note that down as well, Goa to Bangalore and Goa to Mumbai. Okay, note that this is not the TSP tour we are constructing. Okay, this is just for indicative purposes. So next we will have a look at the city Mumbai, and here the minimum ones are Mumbai to Goa and Mumbai to Bangalore, correct?
Yes, sir.
So Mumbai to Bangalore and Mumbai to Goa. Oh, what was the cost of Mumbai to Bangalore? It was 1210. Mumbai to Goa was 590. Okay. Next city we will have a look at is Delhi, and the two minimum costs associated with those are 1540 Delhi to Mumbai, right, and Delhi to Goa, correct?
Yes, sir.
Yeah, yeah.
Delhi to Mumbai with cost 1540 with cost 2080. Okay, and finally we are left with, let's add that, Delhi to Mumbai and Delhi to Goa. Finally we have Bangalore left. So for Bangalore the minimum would be Bangalore to Chennai and Bangalore to Goa. It costs 360 and Bangalore to Goa. It cost 570. Okay, Bangalore to Chennai and Bangalore to Goa. So now we have found the lower cost associated with each of the cities. Note that if we join all of these, this will likely not give us a feasible tour. This will give us something else. Make a note here, there are multiple incoming and outgoing edges at each node, which is not what we want. We ideally want 2 edges associated with each node. Okay, so this is only for indicative purposes, but using this you can get a lower bound on the tour. Okay, so whatever tour you find for the TSP, that will have a cost greater than the lower bound. Okay, and to calculate the lower bound you can sum all these path costs or edge costs that you got and then divide it by 2. Okay, so if you do that you will get the sum will be 8670. If you do that by 2, the reason you do divide by 2 is because you are counting each edge twice, right? Or for each node you are considering one outgoing and one incoming, right? So finally you will have 4335. This is the lower bound, and any TSP2 that you get will have a cost higher than this, unless this itself is an optimal tour, okay, which is usually not the case, but it can happen. Okay, now that you have these edges, you in the next step what you have to do is you have to categorize these edges into 3 different categories. Okay, those are permanently included edges, permanently excluded edges, and default edges. Now let's look at the definition of each of these. For that, let's revisit the information given to us. Okay, so branch and bound starts as a selection of 2n edges. Okay, n denoting the number of cities. Okay, so if we have 5 cities, like in our case, we will have 2n or 10 edges to start with. There are n cities, each city contributes 2 outgoing edges. There are a total of 2n edges that guarantee a lower bound on the cost of the tour. This is what we were discussing till now. the 2n edges represent a partial solution, 0 or more fragments of a tour. Okay, a partial solution represents a set of tours. Okay, is this statement clear?
Yes.
Okay. So essentially what the statement is telling us is that whatever you have till now, okay, that is a partial solution. So this S naught, S0 in the branch and bound, this denotes the set of partial solutions which is constructed by all the edges that gave us the lower bound. Okay, and then you will gradually choose one of the edges, you will add that edge to your graph, and then you will find and then you will branch and decide different partial solutions. Okay, that is how the BNB will proceed, but we'll arrive at that. BNB takes a partial solution and creates two new partial solutions. Okay, one partial solution permanently includes a segment and the other partial solution permanently excludes a segment. Okay, so what this is telling you is that, let's say you started with this initial node S0 where you had all these edges with you, these 10 edges. Okay, we will categorize them into Pi, P and D in some time, but for now assume that you have access to all these 10. So in S0 you have access to all these 10. In the next step, what you will do is you will branch into two directions. You will choose one edge that you want to add to your graph. Okay, let's say you have this graph Chennai, Goa, Bangalore, Mumbai and Delhi. You chose to add one segment here, and this segment can be decided by the lowest available cost. Okay, for example, let's say Chennai Bangalore has the lowest cost 360, so you will choose to go with this one. So you will add another node over here. This will, let's say we'll call A1, and this will say that this definitely has CB. Okay, so this corresponds to this particular graph where you don't have information about the rest of the edges or segments, but you can definitely for sure say that CB will be there. And similarly in the other branch A2, you will say that CB will not be there. So this will correspond to this graph. Where you will indicate this by a dotted line, where you will say that this CB will never be there. So whatever tour you construct for your TSP, that should not include a connection between Chennai and Bangalore. That is how branching will be done. So is that part clear, how branching happens?
Yes, sir.
Okay, great. Now let's go back to our set of instructions. Okay, so we were here. Okay, of the 2n edges, only the edges belonging to permanent segments, permanently included or permanently excluded segments, describe a partial solution. The remaining edges we will call default edges. Okay, they exist only to satisfy the bounding invariant that guarantees a lower bound on the tour cost. So now we will categorize the edges that we had into these three categories. So let's say for this case, for the initial case, okay, for S0, when you had all these 10 edges with you without any semblance of you knowing which you have to definitely include or exclude. So here you are not permanently including any edge. Okay, so here the count of edges is 0. Here you are permanently excluding no edges, so the count of P is 0, and you are having all these 10 edges as your default edges. Okay, which means that they are existing only for you to make sure that each node has two outgoing edges or two linked edges. Okay, this is the configuration associated with S0. Now when you move to A1, okay, here you definitely for sure say that CB is included. So So now this will correspond to this particular graph. Here you are having this permanently included in the graph. And note that this is a segment. And a segment consists of how many edges?
2 edges.
Sorry?
Two.
2, right? Yeah. So, so now your distribution will change. Let me erase this as well. This will now correspond to A1. So permanently included edges will be now 2. And what will be those 2 edges? Can someone tell me?
CB, BC.
Exactly. So the permanently included edges will be CB and BC. So let's make a note of that as well. Maybe let me write it somewhere else so that it's less confusing. Where should I write it? Let's say over here. Actually, let me write down the thing for all of these. Okay, let me erase this. The cost associated with S0 was 4335. Let's note that down. So any cost that we get after branching should be more than 4335. Okay. Now this is the configuration for S0. Let me erase this as well. This is also not required. The permanently included set is nil. The permanently excluded set is nil as well. This is the set of default edges. Okay. Is this part clear? Mohita, I think you were asking a doubt about this one. Is this clear now?
Up to this table, okay, sir. Next one, I have a doubt, sir.
Yes, next one we will discuss just now. So this was for S0. Okay, now let's construct these 3 sets for A1. So A1 says that you have S0, and in S0 CB will permanently be included. Okay, so the set of permanently included edges would be C to B and B to C. Okay, this is essentially coming from the fact that we are including a segment over here, C to B, and each segment is inherently consisting of 2 edges, CB and BC. Okay, permanently excluded edges, as of now we don't have any in this state, right? Because here, let's see, we have you have a restriction on the connection between C and B, but the other nodes, they can take any edges, right? So you have no permanently excluded edges as of now. So this is nil. And default edges, will this remain the same or will this change?
It should be 8, right?
It will be 8, exactly. Because your set of permanently included edges is now consisting of these 2 edges, right? These were initially in the default edge in the S0 scenario, which is over here. Initially we had C to B over here and B to C over here, but these have now moved to the permanently included set. Okay, so the set of default edges will now consist of 8 edges, okay, which is these set of edges. Is this part clear?
Yeah.
Okay, great. Similarly, for this one you will have another distribution of the sets, right? Here you will not have anything in the permanently included set, but in the permanently excluded set you will have C2B and B2C, correct? And the default edges will again be 8 of them, and permanently included set will be nil. Everyone agrees with that?
Yes.
Okay, great. Now let's go back to our information. For each partial solution, which essentially means that for each node of the branch and bound tree, to improve or tighten the lower bound, we infer new partially permanently included or permanently excluded segments that logically flow from the existing segments, PE or PI segments, as demonstrated in the TSP part 1. You can revisit that. And the inferred segments are respectively included or excluded from the partial solution, and we repeat this process until no more new inferences are possible. This might seem a bit wordy, it will become clear in a moment. Okay. When a segment is permanently added, the edges in that segment may permanently replace the default edges. In that case, replace the default edges that guarantee a lower bound on the tour cost, which is what we did over here, right? We knew that C2B and B2C are now in the permanently included set, so we refined our default the default edges set with these few. Okay. And similarly, this thing happens when the segment is permanently excluded, which happened in the other case, right? Other refinement that we had done, or the branching that we had done. BNB refines each partial solution into two new partial solutions until complete tours are formed and satisfy the following condition. A tour must cover all cities. A tour has exactly n partially permanently included segments, correspondingly 2n permanently included edges. Each city has 2 outgoing edges, right, which are the permanently included edges. And for every edge xy, there is yx also in the solution, which also follows from the inclusion of the segment. Okay, now that this is clear, this is also important. Okay, okay, let's go over this for the sake of completeness, because this will be required in the next step. The level of inference can vary. Okay, as in some cases of branching you might be able to infer something extra. In some cases you might not be able to infer something extra other than what you are permanently including or excluding. You have to make a note of that. Okay, and we will use inferences to refine a node, and we have to infer as much as possible as early as possible. Okay, so whenever we take a decision to include or exclude a certain segment, using that inference or using that branching, we will make as many inferences about the next state as we can. Okay, we won't just restrict ourselves to including a certain segment in the graph as per what is given to us. We will see if we can infer anything extra about it. Okay, so we have discussed till A1 and A2. Okay, now we will have a look at B1. Okay, wherein we are also including an extra segment, which is Bangalore to Goa. So let's draw that. I'm not drawing the complete tree. Okay, for the complete tree you can refer to the assignment itself. Oh, by the way, because we are keeping track of the cost as well, what will be the cost associated with A1?
360.
No, I mean the whole partial solution, not just this particular edge.
4335.
Yes, it will be the same cost. So one way to calculate the cost, like you did in the S naught case, right? What you did is for all the 10 edges that you had, right? You summed up the edge cost for each of them and then divided it by 2. Similarly, for the A1 case, can you mute yourself, please? Yeah, thanks. You will include the cost associated with the permanently included edges. Okay, so you will have 360 plus 360 from these. You will include the cost of all the edges in permanently excluded set, which is nil in this case, so no addition, and the cost of all the edges in the default edges set, which is all these 8 costs, and then again you will divide the whole sum by 2. The whole thing will come at the same value because you have not really made any changes to the set as of now. So this will also be 4335. There will also be a cost associated with A2 over here. I'll let you calculate that yourself as per your time. Okay. Now for B1, here the graph that we have been specified is, can you guys see my pencil or should I make it more thicker? Yeah, this should be better. So now you are told to permanently include C to B as well as B to G. These two segments are now permanently included in your in the graph. So let's write down the sets that we have. Permanently included set, permanently excluded set, and default edges set. So what will be there in the permanently included set? Can anyone tell me?
CBBG.
Correct. C to B will be there. B to C will also be there, right?
Yes.
Yes. And similarly, B to G will be there. And G to B will also be there. Okay. Now the question is, will these be the only edges in the permanently included set? I will let you think about it. Okay. So I'll give you a couple of points to ponder upon or think about. First, think about whether these few edges will be the only ones in permanently included set. Okay. Look at the other nodes in the graph that are remaining, okay, that don't have any connections yet, which is M and D. Okay. Second point I wanted to think about is which of these edges have the requirements, which of these nodes, have the requirement of 2 outgoing edges fulfilled. Are there
B
any?
fulfilled, sir.
Exactly. So we should add some edges in permanently excluded set so that we do not add any other edge incoming or outgoing from the node B, right? So there will be some additions in the permanently excluded set as well, and
Yes.
remaining edges will go in the default edges set. So I will give you some time, think about it, about what will be the entries in these different sets, and then we will discuss the solution as well.
No more permanently included, but CGGC is permanently excluded.
Yeah, thanks for that. You are partially correct. I will encourage all of you to think a bit harder. So it's not that visible, apparent to the eyes, But if you think a bit harder about it, you will arrive at some more facts that you need to add to the different sets. Please feel free to share your answers in the chat box or feel free to speak up as well.
DB is also excluded, MB is also excluded.
Correct. Okay, so let's have a look at the edges that will be excluded. Okay, by the logic that we were discussing, B already has two edges associated with it, CB and GB, right? And when I say CB and GB, I mean the segment, so that includes both the bidirectional edges. But for now, let's consider the segment alone because edges might get a bit confusing. So we have CB and GB, right? So we don't want anything more to be associated with B. So we don't want this, and we don't want this, right? So we will add that to the set of permanently excluded edges. So we will add B to M and M to B to permanently excluded set. This corresponds to this segment B to M or M to B. Okay, so let me actually indicate this with the dotted line that we were using to denote things, permanently excluded segments. One more segment that will be put into permanently excluded set would be BD. So B to D will be here and D to B will be here. Okay, which corresponds to this particular segment. Okay, note that okay, let's start from the scratch again. Okay, so now you have these few entries in the different sets that for sure will be there, right? These are very apparent. Now let's try to fill in the remaining edges for each of the nodes. Okay, so let's start with Chennai again. So for Chennai, we already have C to B, correct? We need to add one more edge associated with C. So let's have a look at the distance matrix that we have. What is so Chennai to Bangalore is consumed already, 360 is already in use. What is the next least cost edge from C? CG, okay, which has cost 800. But if we add C to G over here, will this give us a TSP tour?
No, sir.
No, right? Correct. It won't give us a TSP tour, as one of you had pointed out earlier as well. we cannot include C2G anymore because this will create a
Cycle.
cycle CGB, which we don't want. So CG should also be permanently excluded. Okay, so this will include C2G and G2C. Okay, is this clear?
Yes, sir.
Okay, so C2G we cannot add, so but we still need to add one more edge corresponding to C, right? So which edge will we add next?
C2.
Sorry,
C2.
C2M.
C2M, correct, because that is the next least cost edge from C. So the first was 360, then 800, then 1280, which is C2M, right? So we will add C2M, and in which set will C2M go?
Default.
Default, correct. C2M. Okay, great. This is with 1280. This is with, this whole thing corresponds to C2B with 360. This whole thing corresponds to B2G with cost 570.
570.
Yeah. Okay. Okay, so for C we are done. For C, one linked edge is C2B, and the other linked edge is in the default edges set, which is 1280. Next, let's look at the node Goa. Okay, so Goa already has GB connection. It needs one more connection.
GM is also there, sir.
GM is also there. Let's have
Default edges.
yeah. True, that will be there. Let's have a look at that. G2M, which is 590. So we will have G2M with cost 590. Okay. So for G also we now have two edges linked to it, one GB and one GM. Okay. Next, let's look at node B. Now B already has two links associated with it, right? So will B contribute anything to the default edges set?
No, sir.
No, right? B won't contribute anything to the default edges. Next, we will look at node Mumbai. Now is the tricky point in this problem. Okay. See, you have this much partial solution that you know. CBG you know. Okay. Now you have a few possibilities that you can take. Let's say you do something like this. You do C, B, G, and yeah, now you have M and D remaining. Let's say you link G to M. Okay, hypothesis. I'm not saying we are adding it as of now. Let's say you link G to M. Then what will you link D with? Only
M.
C. M is there, correct? M will also be there. And the only thing remaining is C, right? This will construct a tour. Do you agree?
Yes, sir.
Okay. This was one possibility. Let's say there is another possibility. This is there, this is there, this is there, this is there. Now instead of adding GM, let's say you add GD. What are the other two connections you can make for this to become a tour?
DMMC.
DM and MC. This will give you a tour.
Yes, sir.
Are there any other possibilities existing from this point?
No, sir. No other possible.
No other, right? What is common in both these possibilities?
MD.
MD, correct? So irrespective of which direction we take next, MD will always be there. So which set should we add MD to among these three?
Default. No.
No?
Permanently included.
Exactly. So DM should also be there in permanently included. D to M and M to D. Okay. And this has how much cost? 1540. Okay, so let me erase these and update our partial solution that we had till now. This will also be a permanently included segment in this now, DM. Okay. Now let's have a look at Mumbai. So Mumbai already has one connection from DM, so we need to add one more connection to M. And which one will that be? So Mumbai to Delhi is already filled. What is the next least cost edge?
Mumbai, Goa.
Mumbai Goa, right, which is 590. So we will add that to our graph or in the default edges setting. Mumbai to Goa with cost 590. So Mumbai also has two connections now, one coming from Mumbai Goa, one coming from Mumbai Delhi. Now we are left with only one node, which is Delhi. And Delhi also has one connection remaining, one connection already existing, Mumbai Delhi. So what other option will it go for?
Delhi, Chennai.
Will it go for Delhi Chennai? Delhi Chennai has 2190. Delhi Goa has 2080. Delhi Goa is the next least cost edge, right? So it will go for Delhi Goa instead. With cost 2080. Now across all these three sets you have 10 edges, right, with each node having two links. Do you agree?
Yes.
Yeah. So now tell me what will be the cost associated with this partial solution. Remember, what you have to do over here is add all the edges in the permanently included set, add all the edges in the default edges set, sum those, divide by 2.
Three five zero five.
No, you can't have a cost lower than the lower bound that we just got. see here you got 4335, right? Here also you got 4335. So anything that you branch further will have to be will have to have a cost greater than this. Remember to include both these edges, right? So when you include the permanently included segment, you should do 360 plus 360 for CB and BC both, right? So you will have 360 plus 360. Then for BG and GB, you will have 570 plus 570. For DM and MD, you will have 1540 plus 1540. And then you will add all the remaining edges in the default edges set, which is 1280.
4740 is the answer.
Correct. 4740 is correct. So 1280 corresponding to CM, 590 corresponding to GM, 590 corresponding to MG, and 2080 corresponding to DG. And when you sum all these up, this will come to 9480. You divide that by 2 and that will give you 4740. That is the cost of this partial solution B1. Okay, and note that this is greater than A1 and S0. Okay, so if we expand further beyond B1 to C1, that should be greater than 4740 also. Okay, so is the concept of permanently included, excluded and default edges clear to everyone?
Yes, sir.
Okay, so this is how you have to proceed for the rest of the branch and bound tree, and you have to answer questions based on that. So I'm not going to solve the whole branch and bound search tree. I'll let you do that as per your own time, but I have the answers in this slide over here, which you can also obtain actually, because it's a practice solution itself. Okay, so you can verify this when you solve the whole thing. Okay, whatever we just discussed, these are all based on that alone. Okay. Okay. Yeah, definitely. I'll share the recording by tonight itself. Okay, coming to the next part of the discussion that many of you had requested, which is the optimality. Many of you had asked which algorithm will be optimal and which won't be optimal. So what you can say for sure, okay, is that when you can ensure that the heuristic being used is admissible and consistent. Okay, you can find the definitions of admissibility and consistency in the slides. If you can say that the heuristic function is satisfying both these conditions of admissibility and consistency, A star will always find the optimal solution, and this also applies to the variants of A star. Variants of A star will also find the optimal solution as long as the heuristic is admissible and consistent. As for the other search methods, DFS, BFS, all the variants of DFS and BFS that you have seen till now, local search, best first search, all these different methods that you have seen till now, these may or may not find the optimal solution depending on certain contexts of the problem. Okay, so that is one point I wanted to mention. I won't specify or give you any problem for this, but you can verify that using the different graphs that we have discussed till now. Okay, the final thing that I want to discuss is the sparse memory graph search practice, because this was also highly requested and also quite confusing when we discussed this in the live session. Okay, so this is a graph from the previous year's assignments. Okay, same instructions apply. Okay, you are given the true costs along the edges, you are given the start node S and the goal node G. Okay, each cell over here is a 10 by 10 unit cell. You have to use the Manhattan distance to calculate the heuristic associated with each node. Okay, I actually have the heuristic calculated for you so that you find it easier to follow. Okay, so the value written in blue corresponding to each node is the heuristic associated with that node. Okay, and you calculate the heuristic value by calculating the Manhattan distance from the goal node. Okay, using this, the first step that you have to do is you have to construct the A star search tree. Using that A star search tree, you have to apply the smart memory or sparse memory graph search method to tell me the kernel, boundary and open nodes after the first 3 refinements. Okay, first 3 refinements only. After that you can proceed. Once you get the idea, you can proceed in a similar manner, but I'll give you some time to try to construct the A star search tree for this, and then tell me the kernel, boundary and open list for the after the first 3 refinements. Okay, I'll give you some time to try to do that, and then we can discuss the solution.
Is that assignment problem or different problem?
Sorry?
Is this assignment problem or a new problem?
This is the assignment problem from the previous year. I don't
Previous
know.
year.
Yeah, previous year. I don't know if they have this. If you had the same graph in this year, was it the same graph?
That is, I don't have to check.
I think
can't
it was a
recall
different
that.
graph. Let me verify that. This was week 6, right? SMGS.
I think so.
Yeah, it's a different graph. So this graph is new to you. You also need not construct the whole A star search tree. Just construct it till the first 3 refinements so that you can apply this SMGS method and check what will be the open list, boundary and the kernel list for the first refinement, second refinement and the third refinement. You can construct the whole A star search tree later on, and I have the A star search tree constructed actually. You can verify using verify your own solution with that later on, but for now you can focus only on the first 3 refinements. Okay, I'll wait for maybe 2-3 minutes. Okay, any partial solutions till now? So I have the tree constructed for you. Okay, you can verify this yourself later on. Let's look at only the first three refinements. Okay, so the first refinement will obviously be S, right? Let's also try to draw the corresponding SMGS graph. Okay, so S is your starting node, and what are the nodes that you could go to from S? You could go to A, C, I, and K, right? Which is what is listed over here, A, C, I, K. Each of it has a certain cost. The lowest cost is I with 180, right? So I will be expanded next. Let's first note down the first refinement. Okay, so S has links to A, C, I, and K. Okay, let's indicate that S is now closed with this color. Okay, and all these edges, all these nodes that don't have a color inside them, they are supposed to be open. So if we have to define the open list and the closed list, which consists of the boundary and the kernel. By the way, kernel size would be 4 here as well. Okay, I forgot to mention that. So what will be the three different lists based on the first refinement alone? This is the first refinement. Anyone?
I
Yes, I will be in which list?
I, K, S are in open, B in boundary. S in boundary.
I in open.
Yeah, S will be in boundary, correct. All the other 4 will be in open, right?
Correct.
Yeah. Great. So nothing will be in kernel because no such node in the graph as of now that has all its neighbors in the closed list. Okay, that was the definition of kernel, right? Now let's look at the second refinement. These will still be there. Let me redraw this just because we will build upon this. Okay, and S was closed. Okay, now let's look at the second refinement. So I was refined next, right? Because this had the least cost at this level. Let's look at this level alone. Okay, ACIK 240, 250, 180, 200. I had the least cost or least F value, right? So 180 I will be refined next, and because of that these four will be added now. CHLM. Okay, so this C has cost 290, right, which is more than the cost of C over here. So this will be refined with this will be removed with propagation improvement, right? Remember that from A star. So
Yes.
what we have is HL and M, right? So let's add HLM to our graph. Okay, now I will also be in the closed list, right, because I has been expanded. Will anything else be in the closed list?
No.
No, right? So let's update our open kernel and boundary list now. And these two together make the closed list. So boundary will have S and I as well, right?
I2.
Exactly. Why are we including I? Because I has neighbors that are still in the open list. So definition of a boundary node is a node in the closed list that has at least one neighbor in the open list, right? And the open list would be still ACK, oops, and HLM. Kernel will still be empty. Everyone on the same page?
Yeah.
Yes.
Okay, great. Now let's look at the third refinement. Okay, for the third refinement, I won't redraw the graph. I will update it here itself. It will just take time. So third refinement was, okay, don't look at this part of the graph. Okay, this is extra. Just look at this part. You had HLM and till this level. Like just look at this part alone. Based on this, which node will be refined next? M, right? Because it has the least cost 190 among these. Okay, so from M, which is the node that we could go to, so this path is S to I to M. So S to I to M. From M, there's only one way we could go, L, right?
Yes.
And the cost associated with that L is 260. But this is more than the cost associated with this L, which is 215. So this will also be removed by propagation improvement. So actually refining M will not make any changes to the graph. The only thing that we were considering is whether this L to I edge, whether this will be removed and this will be added. But that didn't happen, right? So this L to I edge will remain intact. M will now become a closed node. Now, where should M be placed? This is the third refinement. M will be removed from the open list for sure.
Boundary.
Kernel.
Kernel, right? Because M doesn't have any neighbor that are in the closed list.
Okay.
Okay. So I will stop this refinement at this stage, but I encourage you, please look at the whole tree. Okay, this is there in the slides that I have. I already shared the slides in the same link where all the other slides have been posted, and try to construct the whole SMGS graph. Okay, and construct the open boundary and kernel list at each stage. Okay, so this was all the questions I had for today. I hope these were of some help. I'm really sorry that I couldn't cover all the doubts that you guys had raised over the past couple of uh, live sessions. I have limited time, so one thing that we could do is please post whatever remaining doubts you have. I remember Dhanalakshmi, you were talking about week 9 question 11. Please post your specific doubt in the discussion forum. If Bhaskaran sir doesn't address that, I will address that, whatever concerns the live session, that is okay. Or else you can even reach out to me on email. Okay, I will try to respond to your email. Okay, so yeah, that's all I had from my side. Thanks all for attending all these weeks, and all the best, all the very best for your exam.
Thank you.
Is the answer provided, the whole complete answer, SMGS, the slide?
No, that I don't have. That you have to follow the algorithm and verify yourself. Maybe you can post the solution also on the discussion forum, and I can check the whole solution there and let you know if everything seems fine. Does that sound good?
Yes, okay.
Yeah.
If you provide the answer, it could have better for me. Okay, anyway, I'll try.
Yeah, no, the thing is, I also had the answers for refinements up till the third refinement. So anything more than that, I also have to solve, you also have to solve anyway. So it's better for both of us to solve and very cross-check our answers rather than wait for another answer. Yeah, right?
Yeah.
Yeah.
Agree.
Yeah, my email ID, you can use this. Okay, I've just posted it in the chat box. Mohita, to calculate the cost for each node, you can use the Manhattan distance. Okay, that has been discussed at length in the live sessions as well as the lecture videos. You can revisit that. I'll just show you one example. Let's look at this one. Okay, this R node. Okay, so see the number of hops we have to make to reach the goal node from here. So this is the point you are starting from. You are making 1 hop, 2 hop, 3 hop,
Screen,
4
sir.
hop, and 5 hops. Oh, sorry.
Screen is not visible.
Sorry. Yeah, let me redraw that. Yeah, so you're at this node. Okay, R. You see what are the number of hops you have to make: 1 hop, 2 hop, 3 hop, 4 hop, 5 hop to reach the goal node. Okay, and 5 hops multiplied by 10 because each cell is 10 units in size, so 50 is the heuristic associated with this node. Similarly, you can calculate for the other nodes as well. Okay, then we're already past our time, so yeah, thanks all. And
One general question I have.
yeah,
For the next batch, when is the last registration date? Like that, anything will come to know, or how we can find it out?
for the next semester you mean, right?
Yeah.
I
Any other
suppose
courses
they
we
will.
want to attend means how we will know what is the last date, or it will be shared with us.
I think they should be sharing the details. I'm not sure of the exact timeline though. Maybe at the start of the semester they will share some details with you, or maybe towards the end of the year, around December or so.
Okay.
Just keep
We
checking
will be
the.
receiving mail, or we have to find out on ourselves.
I suppose if you are already registered with NPTEL, you should also receive an email, but just to be on the safe side, keep checking the Swayam page at periodic intervals.
Okay. In generally, which month it will be open? Any idea?
January, if I remember correctly.
Okay.
Somewhere around that time, yeah. But I'm not sure of the exact time.
Okay.
Yeah. Okay then. Discussion forum. Okay. So on Swayam, you will see this Q&A link. Okay. Click on that, and that will lead you to the discussion forum. Okay, I hope that answers your query. Okay, I'll close the session now. Again, all the best to all of you.
Thank you. Thank you so
Thank you,
much.
sir. Thank you, sir.
Thank you very much.